Manufacturers around the world are adopting a digital transformation strategy to help modernise and future-proof their operations. A key component of that strategy is cybersecurity, using defence in-depth principles. What does that mean? It includes strong policies, physical protections, network infrastructure, and securing your equipment. The first step in securing your equipment is to define how secure your machines are, using IEC 62443-3-3, the most robust industry standard, which has common definitions and metrics for quantifying cybersecurity of industrial automation and control systems. This standard focuses on critical requirements such as identity, integrity, authenticity, and confidentiality. Industrial communication standards are required for normal communication between device vendors, so it would be nearly impossible for any control system designer to implement secure communications without the help of their automation device vendors. Enter ODVA. ODVA is a global association comprising the world's leading automation companies. It has been at the forefront of standards development organisations in integrating cybersecurity mechanisms into its automation networks to allow for equipment to be secured. With its community of members, ODVA developed CIPSecurity. To help end users implement cybersecurity measures more thoroughly and quickly, ODVA and its members have authored and released the CIPSecurity specification on Ethernet IP, one of the world's largest industrial automation networks. This video highlights the features of the Ethernet IP confidentiality profile. Banking and email systems have long-standing proven methods of establishing trust cryptographically. Industrial control systems use the same methods. Most vendors that use CIPSecurity embed a certificate in the device to identify it. The certificate can provide a verifiable root of trust. When you're configuring your system, you have control over which machines or systems to trust, such as another single device or an enterprise-level public key infrastructure, or anything in between. When the connection is initiated, a TLS handshake is used to exchange the certificate. This is similar to how web browsers work. These certificates are used to identify the device and determine if trust should exist between the devices. At the end of the process, the devices share a secret key that can be used for secure communications. When you commission the system or replace a device during maintenance, you need to establish its identity. To establish identity, you can either use the device's certificate or use a manual method, which establishes trust using pre-shared keys. This manual method may be simpler to implement for very small systems, although it requires more planning up front. With either method, the secret key can be used to authenticate that each message has been sent from the correct device and that the data has not been modified. The CIPSecurity standard uses the Hashed Message Authentication Code, or HMAC, that is commonly used with the TLS and DTLS communications. If an imposter device tries to send the data, or a man in the middle tries to modify the data, the HMAC will not be valid. Not all automation data on the network needs to be encrypted, so to avoid overhead on the communication process, encryption is optional. If you have confidential process information or secret recipes, you can secure every packet with the TLS and DTLS encryption. CIPSecurity-enabled devices can play an important part in a defense in-depth strategy, helping to fortify the last level of the control system. To learn how you can make your products or systems more secure, contact ODVA or visit www.odva.org.